Okay, in this we're going to look at how we turn a setup like this, which is an electrochemical cell, into a cell diagram, something we can communicate a lot more easily, both in an assessment but also to others who can read them, to go, this is what I need you to set up. So in this what we've got are two half cells, a zinc half cell and a copper half cell. They are connected by a salt bridge with potassium nitrate in it, and we've got a voltmeter, so a multimeter set up as a voltmeter, and it's showing 1.03 volts. So if I was to draw that up on the board, it would take a long time with all the wires and stuff. So instead what I do is I'm going to start at the left and go to the right, and I sort of think of it as a bit of an ABC sort of thing. This here is my anode, so every electrochemical cell has got to have an anode and a cathode. So the anode has to be a solid, so it can be plugged in. The cathode has to be a solid, so it can be plugged in. So what I've got, my cell diagram here, is I've got zinc on one side, and it's a solid because it's my cathode. My anode. On the other side, I've got copper, which is also solid, and they're plugged in. So that's why they have to be solids. So here is my anode, and here is my cathode. Linking them in the middle is this bit of filter paper with potassium nitrate in it. It's got potassium nitrate because potassium ions move really easily, they're motile, and nitrate ions flow very easily as well, they're motile. So in the middle, I'm going to do two lines to represent my salt bridge, because it's separating these two what are called half cells, the oxidation half cell and the reduction half cell. So this is my salt bridge. So you can see I've got ABC. So my anode, my cathode, and my salt bridge. The salt bridge, as I say, is separating two things. Our anode is in our oxidation half cell, and the other side that's being separated by the salt bridge is our reduction half cell. So if you've got half equations, you can work out which side is which. The zinc is sitting in a solution of zinc ions. It doesn't matter whether it's zinc nitrate, zinc chloride, zinc sulfate, whatever. But what we do is, because it's a different state of matter, solid and a liquid, well, aqueous solution, so it flows, we put our zinc with a line between it. That's showing that they're not at the same state of matter or the same phase. The copper is sitting in copper ions, so same thing there, Cu2 plus ions, aqueous. Aqueous and solid are different states of matter. So I put a solid diagonal line between them, and there is my cell diagram for this. The key things I like about this is you can go to all the vowels, anode, oxidation, consonants, cathode, reduction, and that sort of thing. The other thing to know is, and I've done my colours a bit back front, but this one here would be getting more and more positive with its solution, so it's drawing the nitrate across from the salt bridge, but it means it's got extra electrons. Being oxidation, its electrons are a product, so the electrons are going to flow from here to here when it's plugged in through a resistor, a lamp, a bell, whatever it might be, your cell phone. So we get the electron flow goes this way. And as I was saying in the previous lesson, electrons aren't flowing per se, it's the energy they carry gets flowed. They sort of, we think of them as particles, shuffle back and forward. Now this is nice and easy when it's a solid sitting in a solution. But what if we've got a more complex one? What if we have got something where I've got iron 2 plus and iron 3 plus being involved? So I've got my half equations are Fe2 plus, and we'll presume that it goes to Fe3 plus, it might not in this case. And the other one is the copper one. Well, the copper would stay the same. So we still had copper being turned into copper metal. If these were our two half cells, then how do you draw that? And this is where it gets a bit harder. I'll just slide this out of the way because I'm going to go a little bit lower on the board. In this one, the actual setup would be to draw it very simply. In this side, you'd have a solution which has that is 50% Fe2 plus and 50% Fe3 plus. But you don't just shove a wire in there, because whatever wire you put in there is probably going to react as well. So you have to put something that doesn't react. So normally our electrode that goes in there at schools, because schools can't afford platinum, your electrode is going to be carbon. So it's going to be a graphite or carbon one. It's a good enough conductor of electricity, but it won't react with these chemicals. Your copper one will look like the one we had before. You have a piece of copper sitting in there. Any solution will have copper ions in it. So now you've got everything required. How do I do that as a cell diagram? Well, again, I do my ABC, but this time my anode is carbon because it's what would be plugged into. So I write carbon and it's solid, so I have to put my state of matter in electrochem. A line, then I've got these two ions. Which one should I write first? This is where we look at the equation. It's oxidation, it's going from Fe2 plus to Fe3 plus, so I simply write it in that order. Fe2 plus, Fe3 plus. I need to say what state of matter they are, so I put a little AQ because they're dissolved in water. So I've got my A, I've got my oxidation half cell. I now need my bridge, and then the rest would look exactly the same as that one there. So Cu2 plus, Cu. Right. You might see platinum being used in a question. That's much richer people than me. Carbon does the job just beautifully. So that's what we'll usually use in our examples, is carbon. We do find in proper batteries, they do use some other heavy metals that don't oxidize as well. And those are two types of half cells, but they follow that same ABC rule. Anode, bridge, cathode, then fill in the gaps. You might also notice that the way they're written is the way of the equation. Cu2 plus then Cu, Cu2 plus then Cu. Stop that there.